We are very happy to have now a series of lectures with Professor Hermann Nicolai from Max Planck Institute at Golm, near Berlin. And also Hermann was a speaker here in the past. We are very happy to have you here again. And he's going to carry us to the edge of supersymmetry or supergravity and a little bit beyond.
Well, thank you very much. At least one introduction. Maybe I'll get another one in a moment. Maybe. Well, I feel very honored to be here and to open this important 100th anniversary year of Einstein's theory here in Jerusalem. So I thought I'll start out by first telling you what I'm going to tell you. Well, my title is Maximal Supergravity and Beyond. So it's an introduction to supergravity, but with emphasis on maximal. And as you know, there are intimate links between superstring theory and supergravity. And there are two aspects to this. One is that, of course, supergravity theories emerge as some kind of low energy limit from superstring theory. And then the question is, what kind of low energy theory do you get? And then there are all kinds of techniques to study those theories. In particular, the theories that are thought to be important for current phenomenology, models like the MSSM. But this is an aspect that I will not so much talk about, or just where there's some overlap. Rather, I will be concerned with the maximally supersymmetric theory, because starting from Einstein's theory, if you try to make it even more symmetric, supersymmetry is of course the obvious idea, and maximal supersymmetry just means that this is the, at least in a field theoretic sense, the maximally symmetric extension of Einstein's theory. Now for the first aspect, the effective low energy supergravity theories, there are textbooks, very good textbooks actually. To start with, there's the old book by Bagger and Wess, which emphasizes n=1 supersymmetry. More recently, there's been a book by Twan van Brooyen and Dan Friedman, which is more up to date. But also that book stops at n=2 supersymmetry, which is a good distance away from what I want to talk about. Now, let me just say a few words of motivation. Well, as I said, you know about this connection between superstring theory and supergravity theory. These theories live in 10 space-time dimensions. And there are two kinds of theories here, one is called the 2A, type 2 theories, which come in two varieties. Maybe type 2A and type 2B supergravity, which is maximally supersymmetric. And then there's heterotic supergravity, or type 1, type 1 supergravity, which is half maximal. And both, and both of these theories can be embedded into some framework beyond field theory, the superstring theory. So this is thought to be the low energy limit of type 2A, type 2B superstring theory. And this is embeddable in the heterotic string. Now, as you know, probably also know, these are perturbative descriptions. These theories are mostly formulated at the perturbative level. And then another important feature here of these superstring theories that you have left-right factorization. So which means that you can build the relevant supermultiplets by combining left-moving and right-moving oscillators. Now, however, in supergravity, you can go one dimension further, which is T equals 11. This is a maximal supergravity. And that theory is unique. Unlike here, where you have still a little room to maneuver in the sense that you can also choose different gauge groups. This is type 1 supergravity coupled to one vector multiplet, so you have the freedom to, some freedom to adjust what kind of multiplet you want to add. This theory is unique. And of course you can ask, is there some similar completion? And yes, we all think there is. It's something called M theory. And this is, in some sense, well, it's supposed to be the non-perturbative formulation or extension of the superstring. Now, we really don't know what this is. It seems to be a framework. It's some kind of elusive framework. But the question is, of course, can we get a little closer? In fact, there is a candidate, which is supermembrane theory. So this is what you get by going from one-dimensional extended objects to two-dimensional extended objects and try to make it supersymmetric. This theory was constructed by Raksov, Seskin, and Townsend in 1987 or 86. And this theory gives rise to also the SU infinity matrix model, which later also became popular in interpretation as the microdynamics of D0 branes. Now, the trouble with this is that we don't know how to quantize membrane theory, or at least there's very little progress on this. And in fact, this was originally constructed in order to make sense out of this as a quantum theory, but then one had the problem of taking the n to infinity limit, which is also very hard to control. So in this lecture, I will take a somewhat different route, namely, the main emphasis here will not be on this kind of formulation, but the main emphasis here will be on what's called the hidden symmetries, which are duality symmetries that have also played a role in string theory recently. And this was surely one of the most important discoveries in this whole framework by Kramer and Julia in 1979. And what they showed is that when you descend from these theories to lower dimensions, there appear symmetry structures based on the exceptional symmetry series symmetries En, where these where this is in the classification of Lie algebras. Of course, there are the infinite series of orthogonal, unitary, and symplectic, but then there are some exceptional ones. There are the solitary objects in the algebra theory. And amazingly enough, it turned out that all these exceptional symmetries in some sense appear in these maximal supergravity theories. So what I want to do, and what they also discovered, is that the n coming from 11, the n is equal to 11 minus a number of space-time dimensions to which you descend. So in particular for the n equals 8 theory in 4 dimensions, the symmetry that appeared was E7. So this is something I want to explain a little bit. I also want to explain the emergence of these symmetries. And then we would also like to descend even further, because when you descend below 3 dimensions, it turns out that these symmetries become infinite dimensional. And this is really, in my title it says beyond supergravity. And this is really where we try to go beyond supergravity. And this is also part of an attempt to understand or embed the theory, or to explain, in some sense, the emergence of space-time from a theory that has no space-time to start with. And so this is what I will try to explain in my later lectures. So the set of lectures is, so I have 4 lectures. So in the first one, I'm going to say something about, well, some basics of supergravity, basic tools of supergravity. And I will in particular introduce this maximal theory. Then I will show you how to descend to lower dimensions and explain the emergence of these unexpected hidden symmetries of exceptional type. The second lecture will be devoted to maximal n equals 8 supergravity in 4 dimensions, so that's n equals 8. So I will, of course, not explain the full Lagrangian because that would take much too long, but I will give you a basic flavor of some of the essentials that go into constructing this theory. In particular, I will also make some comments on the current the status of finiteness or not, and also say something about ways this theory can be deformed by gauging. And then we will descend below 3 dimensions, where these symmetries become infinite dimensional. And because these algebras are an infinite dimensional algebra of Kac-Moody type, I will give you a kind of mini introduction to Kac-Moody theory. The theory of Kac-Moody algebras. And finally, in the last lecture, I will discuss some work I've been doing over the last 10 years with Thibaut Damour, Marc Hainaut, and Axel Kleinschmidt in various combinations, where we've been trying to understand what happens as you descend to 1 dimensions, where this n becomes equal to 10. So this will be on E10. And as I said, I will try to convey the basic features of this. I will not be able to give you all the details. And I hope to also say a little bit about the incorporation of fermions into this scheme. And let me once again come back to this notion of beyond. This is a duality symmetry, and we have now found evidence that if you really want to realize this symmetry, you have to give up, in some sense, the notion of space and time. So this seems to be a natural framework to formulate a theory that that is pre-geometric, in the sense that you try to do away with space and time in such a way that space and time at some point are supposed to emerge. It's also beyond because there's some evidence that this symmetry is even stronger than maximal supersymmetry. So it could well be that once you really understand this, that the very notion of supersymmetry will be superseded by a stronger symmetry, because this symmetry knows a lot and a lot more than what we learned from supersymmetry. So there's a lot of information here that still needs to be understood. And maybe I should also say one more thing, Maybe you think of supergravity as a sort of closed subject. This is true in some sense that, at least for the low energy theories, that techniques and so on have been developed, how to construct Lagrangians and so on. In these cases, we know what the Lagrangians are. But it seems like once you enter into these infinite dimensional symmetries, this is completely unknown territory. So I would say that at this time, we've just scratched the surface, and there's much, much more to be done. So, and as I said, I hope to give you a flavor of this in my lectures. So much for the introduction. So I will now start with a few basics of supergravity. And the first thing to say is that one has to choose a set of conventions, and it has been said that this is 90% of the work in supergravity. Find a set of conventions that you can trust and believe in and check. This is something no one, this is something you must do for yourself. Because if you look at the literature, there are all kinds of different conventions. And one reason that there's no comprehensive book on supergravity covering all cases from n equals 1 to n equals 8 also has to do with the fact that people have been using all kinds of different conventions. And in order to write such a book, of course, you would have to redo all these calculations in one single set of conventions. So, and that so far nobody has done. So let me just state my conventions just to be definite, at least for this lecture. I will take them from the paper I wrote with Thibault, Dabour, Kleinschmidt, and self, and this is FTH 08 105. In this paper we use the mostly plus metric. So I will use capital indices M, N for will be curved 11-dimensional indices. Indices A, B will be Lorentz or flat. And later on I will use mu nu for, when I talk about the dimensional reduced theories, I will use Mn for the, say, d equals 4 coordinates. And
A and B are the orthonormal indices, right?
Yes, yes, right. Well, I'll be more specific with vielbein and so on in a moment. This is just to state what my conventions are once and for all. I will also use M and N and A and B for internal. So this is when you compactify the, say, 11-dimensional space-time and split it into 4-dimensional space-time, or 3, or 2, whatever. So this will be the indices for the compactified space-time, and these will be the internal indices on the torus or the internal manifold. Yeah. So, as I said, it's going to be, first of all, a description of the toolkit. And the first ingredient here is the so-called vielbein formalism. And I understand that Thibault has already given you some basic introduction to this. So I'm just maybe repeating some of what he said, maybe in a different notation. So, so I hope you don't get confused. So in this formalism, one writes the metric as the square of a vielbein, a frame field, which is like this. So this is local frame, and this is the metric that you find in the usual textbooks on general relativity. And this is such that this index is acted on by coordinate transformations, and this is a local Lorentz index on which you have a local Lorentz group that acts independently at each space time point. So you can say that this object here, it's an element of a coset, so it's a element of the general linear group in d dimensions, and you divide this by the action of the Lorentz group, which is SOD 1 minus 10. And this is a feature that will recur because all supergravity theories, of course, they have this field bind, but also when you come to the scalar sector, the scalar fields are usually also described by such a coset, but where here you have different types of groups. So this is the field bind. Now, once you have the field bind, you can introduce connections. So the connections you get from the so-called field bind postulate, which states that the fully covariant derivative on the field bind is equal to 0, and fully covariant means covariantized with respect to general coordinate transformations as well as with respect to local Lorentz transformations. So we write this equation as dm. I write it like this. So this is the Lorentz covariant derivative. So this is dm dna plus, and then here we have the Lorentz connection or spin connection. AB dnb is equal to, and this is the usual affine connection, gamma, A. So this is the spin connection that I understand was introduced in Thibault's lecture, and this is the affine connection. So you can define a fully covariant derivative by writing this on the left-hand side, and then you have covariantization with respect to the spin connection and with respect to the affine connection. Now, as is also known, one can solve these equations for the spin connections and for the connections in terms of this fundamental field bind. And to do so, one assumes that the antisymmetric part of this affine connection vanishes.
Can you explain one time the previous question? Just why why
I write this on one side and the other.
Equals to.
Yes, I could just as well write it as sorry. You know, I could write a fully covariant derivative by writing this on the left-hand side, and then it's equal to 0, and then this simply means that the fully covariant derivative of the field bind, which contains the covariantization with respect to the spin connection and the standard covariantization that you know from, sorry, you know, if you worked in these fields for so long, there's so ingrained habits, and one of them is to write this on the right-hand side. I'm sorry, but so this straight D is most of the time, by this I mean the Lorentz covariant derivative. So let's assume that the antisymmetric, this is what's called torsion. So this is torsion, which is the antisymmetric part of this affine connection. And I guess this is also in Thibault's lecture, that the affine connection transforms with the second derivative, dm dn. And therefore it's not a tensor. But if you take the antisymmetric combination, then the two derivatives drop out because of symmetry, and then what you're left with is a tensor. Now this tensor in supergravity is not zero. In general, it's a bilinear in the fermions, but for pedagogical reasons and to start with, we take it to be zero, because then you can easily explain how to solve this equation. So then we can solve for omega and gamma. Now I won't do this for the gamma, because this is just the textbook expression that you find. Then you find that this is MNP is equal to 1/2 GPQ 2 times dm GNQ minus dq GMN. It's just symmetrized. So this is standard textbook on general relativity. And this you get by multiplying by another Vielbein, and then simply evaluating and asking that the covariant derivative on the metric be equal to 0. Now you can also solve for the omega, and this you get by now taking the antisymmetric combination and playing a little bit around with these equations. And then you find the following solution. And I also forgot to say that I will also use an inverse Vielbein, which is simply defined by the indices, or with the indices in the opposite order. So this is equal to delta AB. So this is the inverse Vielbein. And then you find that omega ABC, which is equal to EAM omega M BC. So I will freely make use of the fact that I can use these Vielbeins to convert flat into curved indices and vice versa. And then this is equal to the following expression, omega ABC plus omega CAB minus omega BCA, where omega ABC is defined as follows: EAM inverse EBN dm ENC minus dn EMC. Another thing I forgot to say is these are Lorentz indices, and I will use the flat Lorentz metric to pull up and down these indices. So this is what's called coefficient. These are the coefficients of anholonomy. So this means that from this expression, I can solve it, and I can get explicit expressions for the spin connection and for the affine connection in terms of the basic object of the theory, which is the Vielbein, or in the case of the affine connection, I can explicitly express it in terms of the metric. So curvature is then defined in the usual way by commuting the Lorentz curvature, I should say, by commuting two covariant derivatives and letting them act on an object which just has a Lorentz index, and then this is equal to R Mn AB of omega Vb, where Rmn AB of omega, which is just the Lorentz curvature, which is dm omega n AB plus omega m AC omega n CB minus m and n interchanged. So this is just the usual expression for the curvature of a non-abelian connection. So you might ask, well, you've also read about the curvature that can be defined in terms of the affine connection, which is what you find in Landau-Lifshitz and other textbooks. And it follows from this relation, in fact, that that these two are equal. So in general relativity textbooks, one usually finds a Riemann tensor in terms of the affine connection. I assume that Thibaut have you shown this expression or not yet? Well, I'm sorry, I have to overtake you because I have to, otherwise I will never get to what I want to talk about. So this, in fact, if you now express this as a function of the metric, like this, then it turns out that this is the same as EPA EQB R N AB of omega of E. So let me just put you see, this is a relation that if you try to verify directly, if you take the expression from the textbooks or from Thibaut's next lecture and express the gamma in terms of G according to this formula, you get a rather complicated expression. The Riemann tensor is a very complicated function of the metric. Same here, if you take this curvature here and you substitute this solution, then again you get a very messy expression. And if you try to check directly that the two are equal, then you have quite a lot of work to do. However, it's much cleverer to simply say that the Vielbein is invariant under the the total covariant derivative vanishes, because if you take a total covariant derivative that has both this and this is in it, then you get two curvatures and then you get just this identity. So in supergravity, we'll mostly work in terms of Lorentz, the Lorentz curvature, but by this identity, we know that actually this is no different. This is really the same Riemann curvature that appears in the textbooks on general relativity. Now, having said this, I should also add that some of this is going to be modified, because in supergravity, T, M, and P is not equal to 0. And that was certainly the beginning when people tried to make Einstein's theory supersymmetric, locally supersymmetric. There was a source of confusion. It took a while to realize that actually one has to take this torsion into account, and the torsion is going to be some bilinear expression in the fermionic fields. In fact, what happens here is then, of course, that you will have the symmetric part, which will still be given by this, and an antisymmetric part, but then also the omega will acquire an extra correction, which is such that it just cancels in this relation. So this relation is valid in any case, with or without torsion. The difference is only that without torsion, we have the standard expressions for the connections in terms of either the metric or the Vielbein, as here. And whenever there's torsion, then we'll have an extra contribution here, and we'll have an extra contribution here, which is just such that in this equation it cancels. So this also means that the things we know from general relativity, like the Bianchi identity, which states that the antisymmetric the anti-symmetrization over 3 indices of this tensor vanishes is also true here. So we can now, with this, switch freely between these two different descriptions. Okay, now given this, given the Riemann tensor, we can of course define the Ricci tensor, simply tracing. So we have something like MA, which is the contraction of this object with EBN, R, M, N, AB. So this is the Ricci, and becomes the standard Ricci if I turn this index into a curved index by means of the Vielbein. And then, of course, I define the Ricci. So this is Ricci tensor. And then there's also the Ricci scalar R, which is EMA of RMA. And this is equivalent by all this formalism if I take the formula from the textbooks where it's with 2 world indices and I contract with the standard metric. So this is already, so this was the first part of the toolbox. And from this we can now define the Einstein action or Einstein-Hilbert action in the usual way. So that, I guess we can postpone questions to the tutorial. That's
essential.
Yes, of course. So inessential questions will be deferred. So that was number 1. Number 2, now I have to say something about spinors and Clifford algebra. Algebras. So for the description of fermions, we need spinorial representations of the Lorentz group. And for this, we need, as we learned from Dirac, the notion of a Clifford algebra. So we have matrices gamma A, gamma B, where these are Lorentz indices. And they run from 1 to D or 0 to D minus 1. And this is equal to eta AB, where this is the flat Lorentz metric. So this is the Clifford algebra. And we also have to use the Vielbeine again to convert between flat and Lorentz indices and curved indices. So for example, we now define, if we define gamma M with the EMA gamma A, like this, then the corresponding commutator or anti-commutator of 2 gamma matrices will anti-commute or will be twice the metric. So this is the reason we need, well, this is actually the reason that Vielbeine were, frame fields were introduced by Weil, I think, or was it Cartan, repère mobile? Because in the Dirac equation, we have a gamma matrix, and we contract it with a derivative, and the indices are of 2 different types. So this is defined like this. But in order to write the Dirac equation, we have to convert this flat index into a curved index in order to be able to contract it with a derivative. So that's a general feature. And that, of course, is a definition that works for all dimensions. And we will also make use of anti-symmetrized products. And the notation is as follows. We define gamma AB to be 1/2 the commutator, or sometimes I also write it like this. where this notation means that I antisymmetrize in these two indices with the strength 1, which means that if I write out all the permutations with plus and minuses, I have to divide by the number of permutations. So accordingly, we have gamma ABC, which is gamma A, the antisymmetrized product of 3 gamma matrices, which is really like 1/3 factorial, gamma A, gamma B, gamma C, plus, minus, and there are 5 terms, and so on. Of course, the more dimensions you have, the more such matrices you will have. Now, one could again go into a long lecture about what kind of representations are there for these gamma matrices, because it's also important to find out whether there are real representations or whether they're complex. And this has to do with the question whether the spinors we want to describe are self-conjugate, Majorana spinors, or whether Weil spinors, or whether Majorana Weil spinors. And if you look it up in the literature, of course, everyone does it as appropriate for the dimension you're interested in. But this can be also studied in a more systematic way. And rather than now launch into a lecture about this, I thought I would just give you a reference where this is nicely explained. There's an article by Coccaro in Physics Letters, 115b, was 1982. Well, you see, this is already a very old subject because many of the references I'm making are 30 years old. So you see, you have to go fast because otherwise it will not get to where we are now. 389. And what you learn there is roughly that you realize these matrices by building products, and the number of components grows roughly like 2 to the power half the dimension. So in particular, for of course everybody knows that for d equals 4 we have 4 by 4 matrices. They can be chosen real, and for d equals 11 they're real 32 by 32 matrices. Actually, what is the time frame? Where's the chairman? Ah, chairman disappeared. So, why does one introduce these? Well, first of all, because these combinations will appear in the Lagrangians that we will talk about. But these combinations, which are antisymmetrized product of gamma matrices, are generators or represent the Lorentz algebra on spinors. And hence we have the Lorentz covariant derivative on spinors.
Not on any dimension you can choose them to be real.
That's correct, yes. That's explained in this. That this only happens in very special dimensions, for example in 11, and also in 4 you have Majorana.
So in these cases, we can take the spinors to be
Real, yes. Okay. And in supersymmetry, you're of course interested in finding the minimal representation for the spinors. In fact, you know, historically, as a historical remark, supersymmetry was invented, or the first supersymmetric model was Vesenzumino in 1973. And before that, people had tried to construct such a model. And in fact, there were even claims that it couldn't be done. But the mistake was that previously people were not aware of the fact that they're Majorana spinors. It was only realized by Vesenzuminos that you have to impose the Majorana, you have to make the spinor real in order to make the model work and to construct the Vesenzumino model. So in this context, we are interested in the minimal representations. But as you go lower and you have extended supersymmetric series, then you can also have complex spinors. Like, for example, in 4 dimensions, the n equals 1 model, you have a Majorana spinor, but when you go to n equals 2, you have 2 Majorana spinors, and they combine to a Dirac spinor. So as I said, the way this is explained is sometimes a little ad hoc because people just construct what they need, but all of this can be connected to a precise mathematical theory and the so-called Bott periodicity theorem. There's a sort of modulo 8 property here, and it's explained here. Also, in which cases you have complex, in which cases you can have real spinors. But what matters for us is that, I mean, now that we're in 11 dimensions, there is a real representation. The spinor has 32 real components. So the Lorentz covariant derivative is just the usual derivative plus 1/4, that's important, omega MAB gamma AB. The quarter is how to have the same normalization as for the covariant derivative acting on, like here, there's no factor quarter here, but the factor quarter is needed there to get the same normalization of the Lie algebra. And then again, the commutator of 2 such derivatives, Lorentz covariant derivatives, will yield 1/4 the curvature tensor. And again, it will be the same curvature tensor that I showed you before. So, well, as I said, we're sort of trying to assemble a toolbox here. Supergravity is about local supersymmetry. So the supersymmetry parameter becomes a function of space and time coordinates. And therefore, we need a gauge field. And the gauge field of local supersymmetry is the gravitino. The gravitino, which is a vector spinor. So here we have a world index running from 0 to d-1, and at the same time we have a spinor index. And the characteristic property of this is that under supersymmetry it will transform like a gauge field, which means we have a covariant derivative, omega epsilon, and then there may be other terms here. So this is just like the usual variation of a gauge field, except that now the gauge field is a fermion, gravitino, and the gauge parameter is a spinor-valued parameter, spinor parameter. And therefore treated as anti-commuting like all fermionic fields. So of course, again, the number of dimensions or components depends on the number of dimensions which you're in. So in 11 dimensions, which is the maximal dimension, this gravitino, this spinor parameter will have 32 components. So, well, part of the toolbox is, of course, assembling, taking Einstein's theory and making it supersymmetric. So we also have to write some kind of kinetic term for the fermion, and this is the famous Rita-Schwinger Lagrangian. Rita-Schwinger. And with the normalization and our conventions, the normalization is such that here is one, where E, actually I forgot to say this, E, should have said this here. By E, I mean the determinant of EMA, which is equal to square root of minus determinant of GMN. So here we have psi bar m gamma m n p dn omega psi p. This is a term that also appears in all supergravity theories, which complements the Einstein part, which is just the curvature scalar, and then we add to this piece. Now this, as I said, this was originally invented by Rarita and Schwinger to describe spin 1/2 particles in 4 dimensions. And you can already see, so this is, as I said, this is the three, what did I say? 3/2, yes, in 4 dimensions. No, I'm saying this because the notion of spin in 11 dimensions is a little more subtle. Well, 3/2. You're absolutely correct. So here we have this, the gamma matrix, and here we have this antisymmetric, well, this is the antisymmetric combination of gamma matrices. Here we have this derivative acting on the gravitino, and you see this whole thing has already been constructed in such a way that if you just take the derivative part of this at the linear level without spin connection, this will be invariant under these transformations. So this is taking the antisymmetric part here. This is like the field strength in Maxwell's theory, because when you vary it, the variation becomes 0 because you antisymmetrize 2 derivatives. So Rarita and Schwinger just had it with the ordinary derivatives. They were not thinking about coupling it to gravity, but the coupling to gravity is simply a question of making things covariant and compatible with general covariance and also with the local Lorentz group. So this, as I said, this is another term that will appear in every supergravity Lagrangian. Pardon? Psi bar. Now I have to look with the factor of I. Sorry, this is this is where things. Psi bar is simply psi dagger or psi transposed. Really, that's the general definition. So, okay, so we have this. So we now have gravity in any dimension. We have the gravitino. In principle, this is also a prescription that could work in any dimension. So far, no limitations on the dimension. And then, of course, in order to make things supersymmetric, very often one has to add extra fields. And then also, it's not clear that this will work in every dimension, because, from what I said, it's obvious that it seems to stop at 11 dimensions. If you go beyond in 11 dimensions, no one has been able in 35 years to construct a locally supersymmetric theory. So, next thing I want to say is now in order to assemble all these fields into a fully supersymmetric framework, I have to tell you how to count on-shell degrees of freedom, because supersymmetric theory.
You did not say that they have to anti-commute.
The psi's. Yeah. All fermions anti-commute. Or fermions, in my lecture, are always taken to be with anti-commute. So this is actually important. Thanks for reminding me. So we always assume that for the derivation of these supersymmetric Lagrangians, we always treat the fermionic variables as anti-commuting C numbers or elements of a Grassmann algebra. So that means that whenever I pull one fermion through the other, I get a minus sign. These minus signs are actually important when you check the invariance of a Lagrangian, because if you don't pay attention, then you get wrong signs and things will not cancel. But I will not now launch into a discussion what the significance is of anti-commuting C numbers. My view on this, maybe just stated, is that this is just a device to arrive at supersymmetric Lagrangians, but the thing really makes sense only in the context of quantum theory, where these objects become anti-commuting operators acting in some Hilbert space. You know, in the beginning of supersymmetry, there were endless discussions about, you know, should I take this seriously, anti-commuting C numbers, nilpotent, Grassmann algebras, and so on. And this has created a lot of confusion, but I think the best way to think about this is it's simply a tool or device to construct supersymmetric Lagrangians. And at the end of the day, we're going to take this Lagrangian and quantize it, and then these things become properly defined as operators in some state space. So, is there anything else I forgot to say?
Sorry?
Is there anything else I forgot?
No.
Now, supersymmetry requires, so SUSY requires equal number of bosons and fermions. Of bosons and fermions. On shell. On shell. That's very important. So we're supposed to count only propagating degrees of freedom. This is a necessary requirement for supersymmetry, but it's not sufficient. You can try to combine fields in such a way that the on-shell degrees of freedom match between bosons and fermions, but this does not mean that there's a supersymmetric theory, because you can surely also match bosonic and fermionic degrees of freedom in more than 11 dimensions. So that's the first necessary requirement for constructing a supersymmetric theory, and therefore I will have to tell you a little bit about counting degrees of freedom. Because when we assemble supermultiplets, we have to do it in such a way that on shell, when we count the propagating degrees of freedom, the number of bosons and fermions match. This is no longer the case when you go off shell. On shell means that you impose the equations of motion and make use of all the gauge symmetries. Off shell, of course, means that you do not impose the equations of motion, and then very often or usually the number of degrees of bosons and fermions does not match. And then it's a task that has been solved, at least for low-n supersymmetric models, to find formulations where the number of bosons and fermions also matches off-shell. And this is what's called off-shell formulation of supersymmetric theory. However, such off-shell formulations exist only for low-n supergravities, and the maximal supergravities that I'm interested in here, there are no off-shell formulations known for these theories, and quite likely they do not exist. So I will not be so much concerned with the off-shell problem. Maybe I say a few words at some point when I get there. But at the moment, we're just concerned with the matching of on-shell degrees of freedom. Now, how does this go? The prime example that I guess you all know is Maxwell electrodynamics, because you know that a photon in 4 dimensions is described by a vector with 4 components, but on shell there are only 2 propagating degrees of freedom, maybe the transverse degrees of freedom of the photon. And this kind of analysis can be extended to all the fields that are here. So let me just give you a flavor of how you do this and how this construction can be generalized to all these fields. So let's just take Maxwell theory. So Maxwell theory is described by a vector field in any dimension. And in order to parameterize and find out what the degrees of freedom are, I will decompose this, and I will do this in a certain basis of vectors. I will define a d momentum, which is like p as a zeroth component and then some vector component. There will be a p bar m, which is defined by simply inverting the sign of this spatial momentum. This is the momentum, this is the energy. And then we have transverse polarization vectors, EIM, which are such that they're orthogonal to these momenta. Okay, so it's just in momentum space. We're just talking about the free theory. For this analysis, it's enough to look at the free theory. So we simply decompose this like this: A I epsilon I m plus B times Pm plus C times Pm bar. Now, Maxwell theory is invariant under variations, where I simply vary this like this. Well, this is some gauge parameter, which is essentially Pm in momentum space times omega. So using this gauge degree of freedom, I can get rid of this already. And then what I do is I simply work out what is the field strength. Fmn is Pm, or twice Pm with An. Then I expand in this basis, and I now only have these two coefficients, Ai and C. So I don't do this because it will take away too much time. I don't think I need to do this explicitly. And then we simply require that the Maxwell equations be obeyed, which simply states that this is true, the momentum space. And from this we get that C is equal to 0. So this is an easy calculation. You just have to use this decomposition. Also, that implies that p squared is equal to 0. So with this, in this way, you learn that the photon, when you use the gauge degree, the gauge invariance, and you make use of the equations of motion, so you put the theory on shell, this is where the on shell enters, you're just left with this, and that d minus 2 degrees of freedom in this propagating degrees of this Maxwell field. So this is just like what you generalizes what you know from 4 dimensions to an arbitrary number of dimensions. A similar kind of analysis will tell you that if you have a p-form field, which is like AM1 to MP, and the gauge transformation is here dm1 on the gauge parameter, which is a p minus 1 form. So that's like this, antisymmetric. So you can again use this basis to write down a most general expansion. Then you use the gauge degree of freedom in order to set to 0 all the coefficients that are multiplied by the p. And then you impose the equations of motion, which are just a generalization of these Maxwell equations. And then you realize again, you get the proper counting by restricting the indices to be transversal, that is to run from over d minus 2 dimensions. So here, so for p form, the number of degrees of freedom is equal to d minus 2 over p in d dimensions. Yes, of course. Of course. Sorry. Yeah, of course. From this, you define an invariant field strength by acting with another exterior derivative, and then this drops out in the very.
Then you have also to assume something about highest possible derivatives as a Lagrangian.
Yes, of course.
They will
Yes.
express.
Yes.
So
But in these lectures, I will only be concerned with second-order derivative Lagrangian. Yeah, you keep reminding me of all the things I should say, but anyway. So this is the number of degrees of freedom for the p-form field with an gauge invariant second-order in derivatives action. So the same analysis can be done for the linearized Einstein theory. And again, this again goes like this, but of course you now have a tensor and you do it in the linearized analysis. So you write the metric as flat metric plus fluctuation. Okay. Also set all constant equal to 1, like Slava in his lecture. And then you simply analyze the linearized Einstein action of equations. Eta mn are linearized equal to 0. So you write this out what this is. You substitute some such expansion. And then with a little bit of work, and maybe, this is a question we can also, if you really want, we can do this in the tutorial section. Anyway, what you find is gravity is represented by transverse. Again, transverse, which means, again, that the indices only run over transverse, only take the transverse values. But because it's symmetric, I also have to make it traceless. This also comes out of this analysis. Of course, here I cannot take a trace because it's antisymmetric. Traceless in d minus 2 dimensions. So it means the number of degrees of freedom of a graviton in d dimensions is d 1/2 d minus 2 times d minus 1 minus 1 because I take out the trace. So this is equal to d times d minus 3 over 2. So you check that it does give the right result for 4 dimensions. If d equals equal to 4, then it's equal to 2. And this is just the two polarizations that gravitational waves can have. So as I said, the traceless is of course important, and it also comes out of this analysis. And I think this will also appear in Thibault's lecture, because gravitational waves, this is what you get. So finally, for the gravitino, you again make such a substitute, such an expansion. So again, in momentum space, you write the psi m of p as epsilon mi times u I of p, where this is a spinor, plus pmv plus p bar mw, where these are all spinors. So I simply write this object with the spinor indices here. This is a just like what you see in textbooks on Dirac equations, just a spinor. Let me write it out here. Okay. So it's an ansatz which is very similar to this. And you now again exploit the gauge freedom, because we now again assume that the fermions are governed by a first order gauge invariant action. And this allows you to eliminate this piece. And then for the rest, you simply substitute this into the Rarita-Schwinger equation, which follows simply by varying with psi. So it's just this. you have to manipulate a little bit. And then it follows from this. So put theory, so RS equation. And then it follows that W is equal to 0. That's one thing. So that follows like here you get C equal to 0. But you get one extra condition, which is epsilon I m, gamma m, times ui is equal to 0. So that takes away, these are d minus 2 such spinors, because this is a transverse index, but this condition takes away another spinor. So number of degrees of freedom for gravitino in d dimensions is equal to, so now we have d minus 3, okay, times number of spinor components, okay, but then we still need a factor of 1/2 because fermions are described by a first order equation and bosons are described by a second order equation. Another way to say this is momenta for real fermions are equal to the fields themselves, so you get this factor of 1/2. So let's see what this gives. Now we have assembled all we need. So if we have d equals 4, so we have graviton, well, d equals 4, graviton, and we write the gravitino here. So in 4 dimensions, the graviton has, as I said, 2 polarizations. So we write a little lower. So there are 2 polarizations here. And for the gravitino, the number of spinor components is equal to 4. We get the factor of 1/2. And this is equal to 1. So this is also 2. So this means that in 4 dimensions, you can construct a supergravity, or this is at least a necessary condition. We haven't constructed it yet. You can combine the graviton, gravity, Einstein gravity, with a Rarita-Schwinger type graviton and make a supersymmetric theory out of it. Because a necessary condition for this is satisfied, namely that on shell we have then the same number of degrees of freedom. Okay, so d equals 11. I guess I can go on till 10:30, right? We started a little late.
Even 10 minutes more.
Good. Good, okay. So what's the situation in 11 dimensions? If I substitute 11 here, I get 11 times 4, which is 44. So graviton in 11 dimensions, if you have gravitational waves in 11 dimensions, it would be much more complicated to analyze and detect. In 4 dimensions, you just need 2 arms for your interferometer. In 11 dimensions, you would need a few more arms, right? So there are 44 polarizations or propagating degrees of freedom for a graviton. And the gravitino in 11 dimensions, that's 11 minus 3, it's 8. Here we have 32, as I already said. Factor of 1/2, so we get 128. So as you see, it doesn't match. But in 1978 or so, people knew that 11 was the maximum number of dimensions, at least, and this was a result of Werner Nahm's, that if you were to go beyond, then your 4-dimensional multiplet would contain particles of spin higher than 2, which at that time were not, people didn't like. Maybe now it's changed with all this Vasiliev theory. But anyway, so this was the limit here. And then, of course, once it was conjectured that there was a theory in 11 dimensions, which is already, this conjecture is in Nahm's paper, Crémer, Julia, and Scherk sat down and tried to construct a theory. And then they said, well, in order to make it supersymmetric, we need something else, because in order to make this matching. And in fact, they were lucky, because knowing about this formula here, of course, a priori, it's not clear what you should add. But so let's just try 1 form, 2 form, 3 form. And if you take the 3 form field, it's 9/3, which is equal to 84. So you see, 44 plus 84 is equal to 128. So this is the reason when you want to construct a supergravity in higher dimensions, you do need extra fields, because this matching between gravity and the gravitino only works in 4 space-time dimensions. If you go higher, then you need extra stuff. And in 11 dimensions, it turns out to be rather simple. You need just one extra bosonic field, which is a 3-form field. If you do it in 10 dimensions, you know that there are 2-form fields, 4-form fields, and you have to do it in such a combination that, again, with these formulas, you match bosonic and fermionic degrees of freedom. So this is actually, I think they were rather lucky, because, you know, it could have been that it doesn't work. But it just so turned out that there is
What if you have a cosmological constant?
Pardon?
What if you have a cosmological constant? I mean, you started by
Cosmological constant.
flats. You started by expanding about flats. But what if you had a cosmological?
How would you say this? You still have 2 propagating. I would, we live in de Sitter, and we still have only.
Can you define a particle?
Well, let's not get into this, because much of this is based on the representation theory of the Poincaré group. De Sitter is a subtle. Quantum field theory in de Sitter space is. Let me not get into this, because I'm sure I will say stupid things.
No, but
But
the
the
degree
number
of
of
freedom is
Cauchy,
the
the
same.
number of Cauchy.
Yeah, right.
is the same.
Absolutely.
Yes. There's no change. Okay. So, of course, that was just the beginning. Of course, once you have this, you still haven't done the work, because we've now just found a set of fields which are such that on-shell bosonic and fermionic degrees of freedom match. But as I said, it doesn't guarantee that there's a supersymmetric series. So you have to sit down and actually construct it. But before we get there, let me say one more thing. And this is tool number 4, which is dualities between different equivalences, should I say, between different field. Different field representations. And this is very important, because duality, electromagnetic duality, and duality in higher dimensions plays an important role in string theory and also in analysis of supergravity. So let's also approach this subject from a slightly more general perspective. Now, the best known duality is here because of the equality of d minus 2 over p is equal to d minus 2 d minus p minus 2. It turns out that p forms and d minus p forms, d minus p minus 2 forms are equivalent. So how do you see this? And this is also a general feature, And now let me just use, in order to save some time, I will just use form language. If I have a p-form field, then the field strength will be p plus 1 form. So this is equal to dA p-form. Okay. So we have the Bianchi identity. So Bianchi identity, which is simply a consequence of d squared equal to 0. So that tells us that dp plus 1 is equal to 0. And we have the corresponding equation of motion, which in p form language simply means that I take the dual of this. So I contract it with an epsilon. And then I get d star, let me call it star, fp plus 1 is equal to 0. If on the other hand I do this with a d minus p minus 2 form, the field strength will be d minus p minus 1 is equal to 0. And here I have d star f d minus p minus 1. So I can equivalently describe these theories by either taking this p-form field that I have the Bianchi identity and have the equation of motion. These in 4 dimensions would just be the Maxwell equations. And for the dual field, I have this. And now you see that you can relate or equate this to this, because the dual of this d minus p minus 1 form is a p plus 1 form, and same here. And now you see that rather than writing a second order field equation for, say, a p-form field, I can introduce a doublet of a p form and a d minus p minus 2 form, and just write the equation that this is equal to this. And then this will be such that the Bianchi equation for one, or Bianchi identity for one set of p form, or one p form for this p form, will be correspond to the equation of motion for the dual d minus p minus 2 form, and vice versa. So, and this is a sort of characteristic feature of these dual representations, that you replace a second order equation for a p form by 2 first order equations, some sense, by first order let me just write first order equation for a pair. So this is AP. First order equation for a pair of P form and D minus P minus 2 form. The first order equation simply being the statement that this field strength is dual to this field strength. And this, as you can see, if you make this identification, this puts the theory on shell. It enforces the equation of motion, because the Bianchi identity is always valid. It's an identity that follows from the definition, and then you see that you can make this identification only if this equation of motion is obeyed. So the duality is something that works on shell at the level of the equations of motion. So I think this is more or less well known, but let me nevertheless repeat it, because you could now also get the idea that you might also try to do this with a 6 form. In fact, I will show you how to do supergravity also with the 6 form. but it works only on shell. So the final thing I want to say, I still have 5 minutes left. Now for the for these P forms, it's kind of easy because this is something we know from Maxwell theory of the field strengths, dual field strengths. You see in 4 dimensions, it's just vectors are dual to vectors and scalars are dual to 2 forms. But the best known electromagnetic, well, it's electromagnetic duality. We have an electric potential, magnetic potential, and they're related in exactly this way. So you simply take the field strength for the Maxwell field, you dualize it, and write that as the curl of some other potential, and that's the dual magnetic potential. So they're related in exactly this way. Now an interesting question is whether this can also be done for Einstein's theory, dualized gravity. And this is actually an unsolved problem, because the question is, the Einstein's equations are also second order. Can I replace the Einstein equations by such a pair of first order equations, or a first order equation for a dual pair where one field is the graviton and the other field is the dual graviton? Now it turns out that this can be done, but only at the linear level, but only for linearized in other words, I can define this for, if I restrict the Einstein equations to a free wave equation like this, I can introduce a dual potential. And this is where things become more complicated than here, but this is the kind of complication that we will also run into when we now study higher order or the bigger duality groups that will appear at the end of my lectures. So how do you do this? Well, we can check the following thing. This is again something for the tutorials. We now introduce an object which is d minus 2. And it will turn out that the dual object is an object that is no longer a form field, but corresponds to a mixed representation of the Lorentz group. So simply define these as epsilon m1, m d minus 2, pq, and then we have omega n pq, where this is the spin connection, but only the linearized. So I simply take the previous expression, linearize it, and write it like this. Where are we? 2 eta np omega r rq. So I simply perform and define a new field out of the linear. So this is a linear expression in H. It's essentially a curl of this linearized fluctuation. I apply this epsilon, so I dualize it. And then you can check, again for the tutorials, you check that d m1 y m2, and now I have to put d minus 1, n is equal to 0 if linearized Einstein equations are satisfied. So this is a nice little calculation. You first have to calculate what the linearized expression here is. So it's essentially d p applied to h and q and made antisymmetric in p and q. So you substitute this, you substitute it, and you check that this expression, when you act with it, the exterior derivative, you see that this is equal to 0 if and only if the linear Einstein equations are. Yes, that's what I'm doing. Well, yes, that's correct. But I mean, the difference is that there is a difference here. As long as I don't dualize gravity or don't try to do this, these equations are valid also if I couple these fields to gravity in the context of general relativity. So there's no problem, as you will see, in extending 11-dimensional, introducing the sixth-form field in 11 dimensions at the full nonlinear level. The only restriction is on shell. But here, this is strictly true only for these equations, and it even does not work if you put a matter source here and keep gravity linear. Even then, it will not work. And then, from this you conclude that Ymn, at least locally, d minus 2, can be written as the curl of another field, let me call it H tilde M2, to M d minus 2 n, and this is now the dual field to the linear graviton, and this is what we call the dual graviton. So dual graviton. Dual graviton. So that's, to repeat, it's the analog for gravity, or the would-be analog for gravity of the P form dualized into D minus P minus 2 form. Now for gravity, what you get is a field which has H, M1, MD minus 3, N. And now if you decompose it into irreducible representations, then there's a fully antisymmetric part, which is related to this trace. And there's another part of which the antisymmetrization vanishes. And this has the following structure. It looks like this. It's a Young tableau, which has D minus 3 indices here. Okay? So at this, for the first time...
You're below 0.
Oh. Okay. Maybe I can still say two things. Okay. So this is the field that's dual to the graviton, which is symmetric tensor. And if we go to the SOD minus 2 representations, you will see that the counting is exactly the same. D minus 2 transverse, symmetric transverse traceless tensor. Well, maybe I'll continue next time. Say a few more things. So, thank you. Sorry about it.
Is there any questions for Hermann, which are urgent now?
But we have tutorial for questions.
Well, we give
Otherwise
one
I feel discriminated.
Feel discriminated.